let me just have everyone remember the upcoming due dates. So I went ahead and determined a few more due dates here. Estimating a population proportion. This is what we talked about on Monday. That is due tonight. So make sure you do that. What we're going to be talking about today is estimating population means. There's only 9 questions, and some of them are easier than others. So that's due Friday. There's a homework due tonight. There's a homework due Friday, and the quiz is due Monday. So it gives you a nice, I guess, once you finish the homework for estimating population means, then you can go into the weekend, not have to worry about this class, or you can get the quiz over with, and then you really don't have to worry about anything in this class for probably a solid week. It's up to you. But those are the next upcoming due dates, just to make everyone aware. Also, you might have all received an email about filling out my SOTs. So if you can go ahead and do that for me, that'd be nice, because only my second year teaching. I'm still learning a lot. Take the feedback very seriously. If you like what I'm doing, let me know. If you don't, tell me what I need to improve on. And as you know, it's all anonymous, so you can say whatever you want. Besides for that, that's really all I can think of. Does anyone have any questions for me before we get started? If not, then let's go ahead and pick up with the new material, which is estimating a population mean. So in the previous section, we figured out how to estimate a population proportion. And the way we did that, so we took a bunch of samples that we used to ultimately make inferences about the population. So we take all these samples, and then we figure out some measure about each sample. In the previous section, we focus on the population proportion, which is the frequency of some characteristic occurring divided by the total number of observations. And so in this section, we're going to be doing the same thing, but instead of the population proportion, it's the population mean. So really, a lot of the construction is going to be very similar. Because with the mean, we still want to find the point estimate. We still want to find a way to characterize the lower and upper bounds, which means we need to find a characterization for the margin of error. So notions of this are still carried over from the previous section. Well, the point estimate for the population mean is the sample mean. Simple enough. The sample mean, I take a sample of everybody's heights in this class. I add up all the heights and I divide by the total number of people. That's a sample mean. The sample being, I took a subset of people in this class, and the population could be the average height of people who attend Southeastern. So this would be a point estimate for the population mean. Now, there is a problem whenever we look at, because what we did for the population proportion is understanding that there's variability at each time we take a sample. You may get a proportion, as we saw in the last section. You may get one proportion if you do the sample one time. You may get a different proportion the second time you do the study, a different proportion, and so on and so forth. And this variability constructed a distribution. Well, that distribution, fortunately for us, was standard normal. And we just kind of flew through that without really talking about it. Well, there's a problem for doing that with the distribution of the means. If we take a bunch of sample means and find its distribution over doing one sample, we take the average height of this class, the average height of the next class, and the next class, and the next class, put all those averages together, the distribution will not be standard normal. for reasons that I'm not going to get into in this class. So instead, we have to, that variable, since it's not standard normal, we have to rewrite it into something that's standard normal. And basically that just means we want a very convenient form that we can sort of skip a lot of steps on. And this transition is a T distribution, a student's T distribution. And this is a way of rewriting the sample means more so as a standard normal transformation. Now, this isn't really much of a formula. The formula we care about is slightly below here. But ultimately, there is something on here that is helpful. Well, understanding that if the sample size is n, then there's something called n-1 degrees of freedom. And that's probably the most important part of this. Understanding that there's something called degrees of freedom, and it's always going to be one less than your sample size. Because if you printed out the notes, you may notice that there's a new page at the very bottom of the notes here in the appendix. And there's a new table. And this table is a T distribution table. In fact, we'll be referencing it here shortly in the notes. But it's this T distribution table on page, well, now it's 91. And that table requires you to state the degrees of freedom. So, like I said, that's not really much of a formula. That's really just a formality. That's a transformation to make a distribution that's not standard normal into making it standard normal with a bunch of other assumptions that you don't need to worry about. But this distribution here has a bunch of properties that we can utilize. And a lot of these properties should look very familiar. So the properties here, well, because the formula requires a sample size n, then the T distribution is going to be different for different degrees of freedom. Degrees of freedom is just one less than the sample size, so it makes sense that your variable T here, the variable T, will be different for each sample or each sample size that you have, because there's an n in the formula. The T distribution is centered at 0 and is symmetric about 0, just like with the standard normal graph. So again, that's the same thing as the standard normal. If you think about that curve that we had, the mean is 0. And just like with the standard normal curve, the area under the curve is 1. And if you split the graph in half, each side gives you a half. Just like the standard normal one. Again, another characteristic that we are familiar with. As T increases or decreases, the graph approaches but never equals 0. So basically the tails level off at the axes. So all of this should be very familiar except for the degrees of freedom thing. That one's new here. The area in the tails of the T distribution is a little greater than the area in the tails of the standard normal distribution. This is some deviation between the standard normal curve and the T distribution curve. It seems as though the area in the tails of the T distribution is a little bit larger. So it's an approximation of this standard normality. And as the sample size increases, the area in the tails decreases. So there's a homework question. It might be the first homework question that wants you to put in order the area of the tails from smallest to largest. and one of them says standard normal, one says degree of freedom 5, and one says degree of freedom 10. Well, the first thing you would see is that the area for the t distribution is greater than the area in the standard normal. So that means standard normal would be the smallest one in terms of area. And then as n increases, the area decreases. So then the degree of freedom as 5 would be the next smallest, and then, or 10 would be the next smallest and 5. So you would use that information to answer the first homework question. But from all of this, the main thing we are focused on are these formulas down here. So this is constructing a confidence interval. So we're pretty much simulating the steps that we did in the previous section. We're trying to figure out a point estimate and a confidence interval for a new measure now, the population mean. So we're trying to construct a confidence interval for that. And you might also notice 1 minus alpha times 100 again, which basically means the complement of the level of confidence as a proportion, like we did before. And we have these values for the lower bound, the upper bound. And then notice we have a new variable here. Instead of z with a subscript of alpha divided by 2, t is replaced with z, or z is replaced with t. And it says something about the critical value with n minus 1 degrees of freedom. I'll talk about what all of this means in one of these upcoming examples. The first thing we're going to talk about, though, is just determining t values. Now, t values you could think of very similarly to z-scores, very similarly. So we're going to start off trying to figure out just t values, though. So I was going to have this go straight to the calculator, but if you have a lesser calculator, it's not programmed in, and you have to do a lot of steps to program it into your calculator. So I figured let's just make it fair for everybody. So we're going to use the table. So the t value here, they tell us that the area to the right is 0.02 with 19 degrees of freedom. So what we're doing is we're finding the t value 0.02. And we are going to be finding this with 19 degrees of freedom. That part's also important. This tells us that degrees of freedom is equal to 19. I'll show you all how that's relevant here momentarily. So area to the right is 0.02. Degrees of freedom is 19. So let's keep that in mind. Area 0.02, degrees of freedom 19. We go down to the table. Again, this is the t distribution table. It's a new table I've put in the notes. So that the area is 0.02 and degrees of freedom is 19, right? 19. So the way we need to read this, the area is right here. The areas are on the top row. The degrees of freedom, you can see over here, we just go down to 19. Here's 0.02. 19 is here. And we get 2.205. And that's it. That's how you use the table. 2.205. 2.205. Now, something to keep in mind, the table unlike with standard normality, which normally gave us the area to the left of whatever the value is, t-scores or t-values, they give us the area to the right by default. So that's why we don't have to subtract anything from 1 or anything like that. Have to worry about finding the complement area. Now the next problem, let's practice that again just in case. The t-value such that the area is 0.05 with 30 degrees of freedom. So this is the t-value that corresponds to 0.05. So our area is 0.05, degrees of freedom is 30. So we bring that down to the table, 0.05 and 30. .05 and 30. .05 seems to be right here. 30, I have to scroll down a little bit. And we seem to get 1.697. So that's it, 1.697. Okay, so that starts off pretty easily so far, I think. Next thing they want, they change it up a little bit and they ask for the t-value of the area left. So now instead of right, it's to the left, which means we have to do something about it. We have to do something a little bit more. And that's with 6 degrees of freedom. Now it does give us a hint to use symmetry. So let's try to think about what that means. T distribution is bell-shaped. It's very similar to a standard normal curve. Now they want to know the t-value such that the area to the left is 0.05. That's what they want to know ultimately, not the area is 0.05, but they want to know that t-value. We know, though, that the graph is centered around 0. And our table in the back only tells us area to the right. So when it says use symmetry on the other side, we can look at when the area is 0.05. And find this value here. And then on the other side, it has to be the negative. So really what we're going to find is negative t. Because symmetry says, well, t is, let's say the answer on one side is 3, then the answer on the other side would have to be -3. Because we're utilizing the symmetry around 0. So when it says use symmetry, it's basically saying, well, pretend like it's to the right and then just add a negative sign at the very end. That's what it's saying, in other words. So let's look at 0.05 and 6 degrees of freedom. 0.05 and 6 degrees of freedom. And 6 degrees of freedom. So that seems to be right here. So it tells us that the t-value is 1.943. But we have to add a negative to it because they gave us area to the left. We had to find the area to the right and then negate that because we found it on the opposite side. So that's why. So that's the answer. And then part D says find the critical t-value that corresponds to 95% confidence. Okay, so they haven't really given us a level of confidence yet. So to do anything with 95% confidence, we need to find alpha. We did this in the previous section. Alpha is 1 minus 0.95. Remember, it was the complement as a proportion. And so the area is alpha divided by 2. So we need to find T of 0.025 with 16 degrees of freedom. So let's go ahead and look at the table in the back. We have an area of 0.025 and we need 16 degrees of freedom. It was 16, right? Yes. So of course, 0.025 is right here. 16 is right here. And we get 2.120. 2.120. That concludes the first example here. Okay. Does anyone have any questions before we look at example 2? So none of this really looked at the formulas that we talked about at the end of the previous page. Just talking about how to find t-values, but pretty much the examples we're going to look at, it's only going to look at the process we did in parts A and B. So the other ones are for generalized cases, or I guess abnormal cases. So let's move on to example 2. They have a simple random sample of size n. So you have a sample of size n that's drawn from some bigger population that is normally distributed. The sample mean is found to be 106. The sample standard deviation is found to be 10. So think about it as you find a sample, you get that the mean is 106, the standard deviation is 10. So we want to construct a 96% confidence interval around the mean if the sample size is 18. So now they want us to construct a confidence interval. And we construct a confidence interval by utilizing the lower and upper bound formulas that are found up here. Or in other words, we're finding the error and adding that and subtracting that from the sample mean. So what we can do, go ahead and find the error term, which I'm going to take this directly from the formulas here. The error term is T alpha divided by 2 times, I believe that was S over the square root of n. So this is on the implication that we need quite a few things here. We need to know alpha, and they already gave us S and lowercase n here. Alpha is always the confidence interval, well, the complement of the confidence interval as a proportion. The sample standard deviation is 10. That's divided by the square root of 18. Because they gave us the sample standard deviation and they gave us the sample size. And so we can quickly do that division as for the subscript of t, which is 0.02, which means we need to figure out that t value, t of 0.02. So off to the side, we need to find the t value for an area of 0.02 with a certain amount of degrees of freedom. The degrees of freedom is always one less than the sample size. Sample size is 18, degrees of freedom is 17. So that means we need to go to our table. 0.02 is the area, 17 is the degrees of freedom. So 0.02 and 17. So 0.02 and 17. And we get 2.224. So we can go ahead and plug that in up above. 2.224. Two 2.224 times 10 divided by the square root of 18, and we'll get some number out of that, and that will be the error. I'll round this to a couple of decimal places here. I'll put that right here. 5.242. I'll do 3. So that's the error. But just like in the previous section, the error is not our answer. We need an interval. We need a lower bound and an upper bound. So finally, the lower bound, and this comes from the formula above, the sample mean is 106. We found the error to be 5.242. And we can do the same thing for the upper bound. So let's go ahead and figure out those right fast. So that's the lower bound, and then the upper bound is 111.242. That is our interval. That is our 96% confidence interval for the sample means. So we have 96% confidence that really the population mean will fall in between that interval. Okay. Let's look at a different one. It's almost the same problem, but they change n to 12. So they change n to 12. So first, let's find the error term. So that means alpha stays the same. The standard deviation, the sample standard deviation is still 10. And now n is 12. So notice that it only changes one of the numbers here so far. So now we need to go out and find the t-value for the area of 0.02. And you might think, all right, we already have that. There's a problem here. The degree of freedom changes. The degree of freedom is now 11. It's always, the degree of freedom is always n minus 1. And they changed n on us. That's why, that's another reason, or that further supports that the t distribution will change if you have a different value of n. So now we have to go find that value. So 0.02, so the area is the same, but we're going to look at a different row on our table. That's what changes here. So let's go find that value now. So 0.02 and degree of freedom 11. 0.02, degree of freedom is now 11. So now, looking at this row, and it looks like that is 2.328. 2.328. Times 10 over the square root of 12, which we can quickly plug into the calculator. Okay, and I'll round it to about 3 decimal places here. 6.720. And from here, we only found the error, but we still need to construct the interval. So remember the interval, there's a lower bound, which will be 106 minus this new error term that we have. And there's an upper bound. The sample mean plus this error term that we found. So the lower bound is 99.28. The upper bound is 112.72, it looks like. And that is our confidence interval.
So when you see the word interval,
so notice,
you find the lower bound and upper bound.
So did I hear someone in virtual have a question? I don't know if I misheard something. Must be here. So what this tells us is, so notice that our sample size, when we changed it, when we transitioned it from 18 to 12, our interval got slightly larger because we went from 100 and 111 to these boundaries being stretched out a little bit further to 99 and 112. This is because if we have less samples to go off of, we have less confidence in our interval. So we need to expand it a little bit further in order to have more confidence. This is something we talked about in the previous section. As you take more samples, your error decreases because you become more and more confident as to what your central value needs to be. So as you take more as n increases, your error decreases, and that's just intuitively true. Because as you take more samples, you get more of a feel for what the population looks like, which means you will find your interval values getting closer and closer together. So if n here was 1,000,000, you'd probably find that your error would be maybe 1 or something instead of 5 or 6 here. So let's see what happens. Let's try and change part A again, but instead of a 96% confidence interval, let's do a 70% confidence interval, but the same sample size. So I guess intuitively, does anyone think they might see what might happen to the intervals? I think the intervals are going to stretch out for a 70% confidence interval or get really compact. And if you don't know, it might be worth thinking about as I work this one out. If you're less confident in an interval, do you think that's going to encapsulate more or less? Yes, let's find out. Well, because they're changing this to a 70% confidence interval, we need to find a new alpha. Alpha is 1 minus 0.7. Remember, alpha is always found from the level of confidence. So that's 0.3. We can go ahead and find that error term. So it's 0.3 divided by 2 now. Because remember, it's alpha divided by 2 in the formula, times the standard deviation, which is still 10, divided by the square root of lowercase n, which is 18. So that's really t of 0.15 times 10 divided by square root of 18. And we need to find this t value with the degree of freedom equal to 17. Because here n is 18. So you always subtract 1 from it. So 0.15 with a degree of freedom 17. Let's go look that up. 0.15 degree of freedom 17. Okay, so 0.15 is right here. Degree of freedom, 17. It's 1.069. So 1.069. Let's go ahead and bring that up. And we can quickly go ahead and put this into the calculator. 1.069 times 10 divided by the square root of 18. And rounded to 3 decimal places, 2.520. It's actually what it rounded to 3 decimal places. That's what it would come out to be. But that's not the answer. That's the error. We need a confidence interval. 2.520 is not an interval. It's just a number. But this already answers the question I posed at the beginning of this part. Notice as our confidence decreases, our error also decreases. So something interesting to keep in mind. You would be less confident about a more precise interval. you'd be a lot more confident about a larger interval. But alas, the lower bound is yet again 106 minus 2.520, and the upper bound is 106 plus 2.520. Let me fix this up a little bit. There we go. Okay, so let's go ahead and figure out these real fast. 106 minus 2.520, 106 plus 2.520. 103.48, 108.52. And that is our 70% confidence interval. So we are 70% confident that the mean will fall within this interval. It's a lot more precise of an interval, but we have less confidence about this precision. And then to answer the next part, can we compute the confidence intervals if the population had not been normally distributed? No. Population must be normally distributed. So we cannot compute these confidence intervals without a normal distribution of the population. And this is inherited by some of the assumptions we made in order to get the transformation to the t distribution. It makes a few assumptions there. In fact, t distributions, they were invented by a guy who worked at Guinness Brewing Company. That was kind of interesting. So a beer guy came up with the formula. But that was kind of cool. Okay. Does anyone have any questions about that? If not, we also need to figure out how to determine an appropriate sample size. We did this at the end of the last section. You need a certain sample size to, I guess, estimate the population mean with a particular level of confidence within a specified margin of error. So notice this is pretty much the formula that we had above in a sense, but we're solving for n. So, and notice there's also a z. The z is back. And there is a reason why that I'm not going to get into, but it's no longer a t there. There is intentionally a z there. So that's a z-score now, which means we would use inverse norm like we did in the previous section. So let's talk about how to use this formula here in this example. So a researcher wanted to determine the mean number of hours per week the typical person watches television. And they give us the sample mean, or the sample standard deviation, rather. How many people are needed to estimate? So as soon as you see how many people, it tells you are solving for n. So within 2 hours with 95% confidence. So the formula we're using, now the z with the subscript of alpha minus 2, I talked about this in class as we can use the inverse norm for this. But you have to use 1 minus alpha divided by 2. So I talked about this in class for the last section. Anytime you see z with a subscript, times s divided by e squared. So that means we need to figure out alpha. We already know little s, and we need to figure out the error. Well, the inverse norm, we need to figure out what alpha is. Alpha is the complement of the confidence interval as a proportion. Oops. There's a divide by 2 there. 0.05 divided by 2. The sample standard deviation was given to us as 7.5. And all of this is divided by the error. All they tell us for the error is within 2 hours. That's all they say. So that means our error is actually just 2. That comes from within 2 hours. So we can use 2 for within 2 hours. And we square that. And whatever the calculator tells us after this messy computation, that's the number. So pretty much we're doing exactly what we did before. Oh yeah, and don't forget parenthesis around this whole thing because we're going to have to square it. Divided by 2, close parentheses, and square that. And of course, inverse normal can be found under second and VAR's distribution. And we get 54.02. But we're dealing with number of people, so we need to round this to an integer. Just like we did in the previous section, we have to round up to the nearest whole number, no matter what. So we have to round this up to 55. They just make us do that. Yours is not set up that way?
I was having trouble doing the whole last night with the student night because there was like one where you had to like divide it by the 3 and I didn't know how to put that in the new calculator.
So divided by the 3.
Like you see how it has divided by 2? Like whenever I do that on my calculator, it doesn't look.
Did anyone else get this?
Whenever I click inverse norm on mine, it goes straight to that.
Yeah, I talked about that last class.
Oh, yeah, okay. Yeah, I remember you talking about it, but whenever I was trying to divide, I couldn't figure that part out.
You gotta divide by 2.
I divide by 2 after. Like once it gets to this.
No, you divide by 2 in the inverse norm.
You do?
Yes,
Yeah,
because that is part of the.
I thought she was talking about the 2 like underneath. That's what she's talking about.
So this is what you have to have for the area.
Yeah, and then you do the divide by 2 after and you put that in.
So there's let me go back to that. You have to have 1 minus 0.05 divided by 2 there to match up with what's in the parentheses there. And then inverse normal, they close the parentheses for you. So times 7.5 divided by 2. And,
Oh, that has to be divided by 2 also?
well, we're dividing the whole product by 2.
And since they close parentheses, you also need to divide that by 2.
Yeah, ultimately, so yeah.
Okay.
Well, that 2 in the denominator is different than that 2 in that denominator. I know that
Oh.
sounds kind of weird.
Right, I see what you're saying now, okay.
And you get this, but you still have to square it. So we get to square it. Yeah.
Okay, but I got 561, you got 54.
Yeah, okay, so for this.
I did that the first
time.
time.
Times 75. You would put that after, right? Times 7.5.
Yeah.
Someone's asking me a question.
Right.
Okay, I got 54, that's right.
I couldn't,
So you have to do the times 7.5 and then divide by 2, and then close parentheses and then square.
Inverse norm. Well, maybe Kevin's advice might be helpful. Second in catalog, yeah, you can't always do that. It just takes forever scrolling to it, but you can do it. Or yeah, you can follow the advice. Just wondering why yours is being first.
That was really good, I thought. Calculator last time.
Oh, there's two inverse norms here. It took your result from before, and then I just put on an extra inverse norm. Oh, so that's, all right, so let's try that again. We just had a whole bunch of inverse norms stored on there. Ace times 7.5 divided by 2. You still have to square that. There we go.
Okay.
All right, that was fun. Emily has come along.
I can't read what he wrote up there. I think I have to do that.
I can't read it either. You can hit second and catalog. I can show you what he's talking about. Basically, if you want to do it the way I'm doing it.
Yeah, I don't like them.
Second
He's saying,
catalog.
yeah, if you go to second and catalog, it lists every command this calculator has.
Oh my
But
God.
instead of scrolling all the way down to inverse norm, you would press second, and there's a little, actually not second, you press alpha, I believe, and just the letter I. No, I thought, oh yeah, it does work.
Okay.
And then it just brings you to the I's, and then you can scroll down to inverse norm. That is so you can do it the way I have it.
Okay.
Instead of it saying area, mean, standard deviation. I don't know.
Just click inverse norm.
So yeah, Kevin, your advice is good too. In fact, I used the catalog for some command. Can't remember, binomial, I think it was, PDF.
So once I get to inverse norm, I just click enter.
Yeah, and it should be set up, if you do it the way Kevin here mentioned, it'll be more consistent with my calculator.
It doesn't do that every time. That means I have to scroll every time.
Well, that's why you have to press alpha and find the I letter.
What's it? Oh, like ABC, that.
Yeah, so it'll let you skip to the I's.
That makes sense.
Yeah, because I would love to use the catalog every time because that would be consistent across every calculator, but I don't know, figured people might not want to scroll, but that is a way to skip down. Again, that's another situation where the calculator tries to be, in their newest installment of the calculator, they try to be more helpful, but it ends up being somewhat more complicated for some others. So it's kind of a give and take. But I think we can all hopefully agree on getting 55. Well, I guess let's practice it. The next problem, it's within 1 hour with the same level of confidence. So really the only thing that changes here, the same level of confidence means the same alpha, 1 minus 0.05 divided by 2 times 7.5 divided by 1 now, because it's within 1 hour, and that's all squared. So maybe that'll be good practice. See if we can all get the same answer for that one. Or I'm just going to cheat, press second and enter. So again, it makes you round up. So the only thing that changes is that, your error is even smaller. So now you have to be more precise. So the only difference between what I have on the top of the calculator and what I just typed in is the 2 and the denominator became a 1. Is anyone not getting 216?
I didn't get
I had 25 the first time and 37 the next time.
I don't think I can do it.
Oh yeah, because you have to, all right, so if you do the inverse normal way, the way Kevin said it, you have to close your own parentheses. So in your case, you have to close off the inverse normal here. You have to stop it right there.
Okay,
Yeah. If you do it using the catalog, you have to close off your own parentheses. If you don't, it'll just state that your area is encapsulating everything you type afterwards. What do you do?
I got it.
You got it?
She's fixing it. If she knows how to do it, she'll teach me, but
Yeah, I figure if I help one of you, that's pretty much the other one. You forgot the parentheses in the very beginning, but you can fix that. Actually, you can fix it. Second and insert brings back what you had all the way to the front. Second and insert, then you don't have to type anything. Yeah, for the virtual people, if you do it the way Kevin says, you have to close your own parenthesis. So you have to, if you go to catalog and you put an inverse norm, you have to close off the parenthesis after 1 minus 0.05 divided by 2. If you do it the way if you go through your calculator's distribution menu, it will close off the parenthesis for you. So it's something to keep in mind. Okay. So part C is asking what happens when you double the accuracy? Because we went from, I know it might sound weird at first, from 2 hours to 1 hour, which sounds like, isn't that half? Well, we're dividing by 2, so that's really 1/2. And then what's twice of 1/2 is just 1. So we are doubling the accuracy here. So what happens, our results pretty much quadruple. What's that?
I'm saying more people.
Yeah, ultimately, well, yeah, it's the number of people quadruple. I believe that's what it says in your homework. It uses that terminology. Quadruple. That is how you spell quadruple.
I do not think so, but I don't know how to spell it, so we'll have to put it.
I'm pretty good at spelling, but I can't remember quadruple. I intentionally have spell check turned off on my typing software, and it does help, but I spell guaranteed wrong every time I type it.
I spelled definitely wrong every time I type it.
Definitely.
Cannot be weird.
Yeah, there's always a few. I think everybody's got a few words they just cannot remember for the life of them. Okay. How many people are needed to estimate? So this is same problem, but notice they change within 6 books. So E is 6 and 99% confidence, which means that alpha is, well, 1 minus 0.99, which is 0.01. But it goes straight back to the formula. And again, let's all see if we can do this now. And if you're good with the calculator, you can just press second and insert, so you don't have to type in everything again. Wait, what did I put in 0.05? That should be 0.01, I'm sorry. Yeah. Make sure you change that. 0.01. Is there anything else I'm missing? All right, that should be it. 0.01 divided by 2 divided by 6 divided by 6. 1 minus 0.01 divided by 2 times that divided by 6. Really, we get 11 because you have to round up the 10 to an 11. You got it? Cool. So I guess from there, compare that result to part A. How does this affect the sample size? Well, it seems like it decreases. How does increasing the level of confidence? See, I feel like this problem should have been, the error should have stayed the same. Oh, notice what I did. I confused two problems together.
When I did mine, it said error. But I typed it in the same way as the last one.
Give it to Noelle. She's good at it. My leg, I kind of hurt my leg yesterday. I'm trying not to walk as much.
I'm glad you're messaging me. We're good. What are you gonna get knocked out? I was like, are you kidding me right now?
No,
That's your excuse.
no, I jogged a little too hard yesterday. My leg hurts, which makes me sound old. I'm not old, but oh well. So notice what I did. I talked about television, and then I'm talking about books. I mixed up two examples. I tried doing that to resemble the homework, and well, I guess if I really want this to make sense, I would have to change 6 here. Instead of 6 books, I would have to make that 2 books. Or no, 2 hours. So really, this is just it's not a bogus problem, but it doesn't illustrate the point that I want to make. 2 hours. So really, E is 2 in this problem. This will really help us illustrate the point that we try to make in part E. So I'm changing problem D here to 2 hours. So that shouldn't say books, that should say hours of television. And of course, it's not going to be read, it's going to be watched. To be consistent. Then E is equal to 2 hours. Okay, so let's get a new number. So it's not 11. I'm just changing the problem. But you don't have to type in everything again, because you can just press second enter. Only thing you have to do is instead of divide by 6, divide by 2. Yeah, so that would be 94. 93.30, I'll just go ahead and write that, which we have to round up to 94 no matter what, because the formula makes us do that.
So then E would be as the confidence increases, so does
As confidence increases,
the amount of people, huh?
amount of people increases. Yeah, we wouldn't have seen that point from the 6 hours that I had before. Because to be more confident, you need a wider interval. You're less confident about a more compact interval. You're going to be more confident about a wider interval. So that's the point I wanted to make. Okay. Well, that was fun. Does anyone have any questions?
I have a question on the homework. She's got the same one as me.
Okay, so what's going on?
On the homework that's due tonight.
Can we talk about it after class? I need to go over the rest of the test.
Oh, that's why we did it early.
Yeah, it's never that easy. Can't let any class time go to waste. Who will do that? Yes. Leave everybody else have their test here. Okay. So I wanted to go over the test here. All right. All right, so I think we're picking up from on page 7. So a recent poll shows that 65% of this. There's a random sample of 15 adults. So this is a binomial distribution, or a binomial probability. So with that, because it says exactly 10, then that means x is equal 10, which means you use the PDF version, which is always n, followed by p, followed by x. At most 7 means x is less than or equal to 7, which means you would use the CDF option, 15, 0.65, 7. Remember, you use CDF when it's an inequality. More than 6, a lot of people got this one wrong. When x is greater than 6, well, you need the inequality to face the other direction. So the complement would be x is less than or equal to 6. That's the complement of that. And anytime you complement, that's 1 minus the binomial CDF of 15, 0.65, and 6. Anytime you complement, you have to do 1 minus. I think I gave you a point or so extra if you did the 1 minus. Remember to apply the complement, because you have to have the inequality face that way. For problem 6 here, oh, I almost forgot.